All right, Giancoli 4-7. So if we're going to solve Newton's laws problems, we got to draw free body diagrams. First, we draw a sketch, right? And then for each object, we draw free body diagrams showing all the forces. We want to try to make numbers and directions as accurate as possible, label the forces. Obviously, get multiple objects, separate diagram for each, and we'll get into some of those. Any vectors, we want to resolve into components. And then once we do that, then we want to use Newton's second law. And again, there's plenty of demonstrations, and I'm just going to demonstrate a few, and there are others. And then, of course, we solve using math. Examples. Here's two boxes, and we will solve this problem in a little bit later. But we're pulling with a force of 40 newtons of two boxes, one with a 10 kilogram box and a 12 kilogram box. And this is tension. Here's your force applied. Here's the tension force in between. And just understand that the tension is going to be the same throughout this string. So the tension on this box is going to be the same as the tension on this box. We're going to do example 4.9 now, adding force vectors. Calculate the sum of the two forces exerted on the boat by workers A and B. Do it now.
All right, we're just adding force vectors. We're going to calculate the sum of the two forces exerted on the boat by workers A and B. So this is worker A, and this is worker B, and this is very similar to adding vectors. We're essentially going to add this vector to this vector. So what we're going to do is we're going to break this first one. So I'm going to say A, all right, and I'm going to break it up into its components. And my angle's 45, so this is 40 cosine 45, and this is 40 sine of 45. And then for B, same thing, okay, and I'm just going to make it like this, okay. I guess my angle's going to go this way, so I better keep it this way. So I'm going to have a negative. My angle's 37, and this is 30 newtons, so this is 30 cosine 37, and this is 30 sine of 37. That's going to be negative. So now I take my x's and I add them together. So I go with my calculator, 40 cosine 45 plus 30 cosine 37. And my x, when I add those two up, my overall x is going to be 52.2 newtons. And then my y, and it's in the positive, and then my y, I'm going to go 40 sine of 45 minus 30 sine of 37, subtracting because it's going down, and I get a positive 10, so it's going to be just a little bit up here, 10.2 newtons. Then to find my resultant force, Pythagorean theorem, 52.2 squared plus 10.2 squared, square root of my answer gives me 53.2 newtons. So that's going to be the net force. And then to find my angle, again, I'm going to use tangent. Tan theta equals opposite over adjacent. So my theta is going to be my inverse tan of my ratio, 52.2. So inverse tan of 10.2 divided by 52.2 gives me an angle of 11.1 degrees. So 11.1 degrees north of east. So that's what my resultant's going to look like.
Conceptual example. Here's a hockey puck. The hockey puck is sliding at constant velocity across a flat horizontal ice surface that is assumed to be frictionless. Which of these sketches is the correct free body diagram for this puck? What would your answer be if the puck slowed down? So we have a frictionless surface. So the only force acting on it should be up and down because we'll be going at a constant velocity. Our left and right forces should be balanced, and this is the only one that has that. So normal force and gravity are all that's there, with no friction nor applied force. Now, what if the puck slowed down? if we're moving to the right, right, and we want to slow down, that means our acceleration has to be to the left. So where's our force going to go to the left at? This one. So if the puck's slowing down, it'd be this one. If our puck was speeding up, it would be A. Example 411, pull in the mystery box. Suppose a friend asks to examine a 10-kilogram box, guessing to hope what is inside, and you respond, sure, pull the box over to you. Pulls the box by the attached cord at the 40 Newton force at a 30-degree angle. We're going to calculate the acceleration and the normal force from the table onto the box. We are negating friction here. Do it now.
All right, example 411. Suppose a friend asks to examine the 10-kilogram box, hoping to guess what is inside, and you respond, sure, pull the box over to you. She then pulls the box by the attached cord here, and the diagram's on the problem. Along the smooth surface of the table, the magnitude of the force is 40 newtons at a 30-degree angle. So we want to find the acceleration of the box and the magnitude of the normal force on the table. We're going to assume that friction is neglected. Okay, so no friction yet, right? So first thing I want to do is draw a free body diagram. So I have my box, right? And my box has gravity there, normal force that's pushing up, and then I have this applied force. Now this applied force is at an angle, but we're going to break it apart into x and y. So we're going to take the applied force and we're going to break it up into the two parts. So the x component is going to be 40 cosine of 30. Right? That's our applied force in the x. And then our applied force in the y is 40 sine of 30. And now I have my forces. So A wants to know the acceleration. Well, we're pulling this way. So when I talk about the acceleration of this case, I'm worried about just what's going on in the x. So in the x, my net force is equal to ma. The mass of my box, I think we said, is 10 kilograms. My net force is going to be this only because that's the only force I have. So 40 times the cosine of 30 times a. So divide by 10. The acceleration of my box is 40 cosine 30 divided by 10. I get an answer of 3.46. Okay? So I just used the x component of my force. Now, to find my normal force here, the first thing I can do is I can solve for the force of gravity, mass times g. My mass is 10, g is 9.8. So I know the force of gravity is 98 newtons. But it's the same equation, right? Sum of my forces, net force is equal to ma. So I got two forces going up. I got normal force, and I got the y component of my applied force, which is this. So those two are in the positive. So 40 sine of 30. And then I have the force of gravity going down, which we have already quantified to be 98. Since it's going down, I'm making it negative. That equals ma, which is 10 times a. Okay, 10 times a. So then I look at the y. My object's sitting flat and going this way. My acceleration in the a, right, is going to be 0. So 10 times 0 is 0. So I'm going to get Fn plus 40 sine of 30 minus 98 equals 0. I can solve for Fn is equal to 98 minus 40 sine of 30. So then I just do my math, 98 minus 40 sine 30, and I get 78 newtons. So the new normal force, or the normal force while I'm pulling, is 78 newtons. Big key to this, keep your x's and y's separate. If you pick up positive, which I would normally do, down will be negative. So when you sum your forces, make sure your up forces are positive and your down forces are negative. And then lastly, if you're accelerating in the horizontal, the vertical, you're not accelerating at all. Make that acceleration 0. And
then it just turns into an algebra problem from there. Let's say we have a 10-kilogram box. We're dragging it on a frictionless surface with a horizontal force of 10 newtons, so strictly horizontal. If the applied force is doubled, so if we double to 20 newtons, the normal force on the box will, well, of course, the answer is B, remain the same. Normal force is just based on the opposite of the force of gravity, and we're not doubling the mass, we're doubling this. So if the mass stays constant, so will the gravity force, which means our normal force will remain the same. So B is the answer. Example 412, two boxes connected by a cord. Two boxes A and B are connected by a lightweight cord and are resting on a smooth, frictionless table. They have masses of 10 and 12. This is one we saw earlier. We're pulling with 40 Newton force on the 10-kilogram box. So we want to find the acceleration of each box, which will be the same because they're attached. And then B, the tension in the cord. So we want to find the tension in this cord. Do it now. All right, 412, two boxes connected by a cord. Two boxes, A and B, are connected by a lightweight cord and are resting on a smooth, frictionless table. Fantasyland. The boxes have masses of 12 kilograms and 10 kilograms. A horizontal force of 40 newtons is applied to the 10-kilogram box. Find the acceleration of each box and the tension in the cord connecting the boxes. So I want to find the acceleration and then the tension in the cord. First step, draw free body diagrams. Thought I had my different colored marker. Here it is. So my free body diagrams are for each box. So I'm going to do this box. I got normal force and gravity. I got the applied force. And then I have a tension force here. Okay, so this is box A. Box B, I have its gravitational force. That's being negated by the normal force, but I also have the same tension going here. Remember, tension's the same in both cords. So let's write out Newton law formula for each. So for box A, these two balance out, so I'm only worried about the horizontal. So my sum of my forces is equal to MA. I want to make this positive. Force applied minus equals MA. And then for box B, sum of my forces equals MA. I only have one force, that's a positive. FT is equal to MA. Now I'll substitute what I know. I know my applied force is 40. So 40 minus FT equals mass of this box, which is 10A. This one, FT, I don't know, but I know my mass is 12A. So I have two equations. Quickest way to do this, and it's not the only way, is to take this equation, FT is equal to 12A, and this is FT, is substitute. So I'm going to substitute 12A in for FT. I got 40 minus 12A equals 10A. Add 12A to each side. 40 is equal to 22A. I divide both sides by 22. And I get an acceleration of 40 divided by 22 of 1.82. So that's the acceleration. Now, since the boxes are attached, if this one's accelerating at this rate, so is this one. Okay, so they're both accelerating the same. So to find my force of tension, I just take my acceleration, substitute it in here. I go 12 times 1.82, and I get a force of tension of 21.84 newtons. If I took this and put it in here, I'd get the same answer. So I just substituted here because it was easier math. In this example, we're looking at an Atwood machine. Another two-body problem with a pulley. So what we have is we have an elevator car going down. We have a counterweight going up, okay? And our goal is A, find the acceleration of the elevator, which is the same as the acceleration in the counterweight, and then the tension in this connecting cable, which will be the same throughout the cable. So the tension on the counterweight will be the same as the tension on the elevator car. Do it now. All right, so here we have the elevator with this mass, okay? And then we have the counterweight of this mass. And the question we have to ask ourselves is, one, which direction is this thing going to go? 1,000 to 1150. It's going to go this way with this being a pulley system, right? So this is going to accelerate down, and that's going to accelerate up. Hopefully that makes sense just by weight, just what you know about counterweights, right? So now with that, I want to draw free body diagrams for each of these. So for this one, here's what I got. I got tension going upward, because that's the strings attached, and I have gravity going down, okay? For this, I have gravity going down and tension going up. And as we talk about tension, we just have to remember tension's the same throughout, so whatever the tension is here, it's the same as it is here. So let's talk about this one first. Since my acceleration is going down, I'm going to make this side positive and this side negative. Not necessarily, you don't have to do that. If you want to keep top positive and everything going down negative, you can do that. I'm going to do this, but any way would work. Either way would work. So I'm going to say the sum of my forces equals ma. So my forces together are Fg, right, which is m times a, which is 1150 times 9.8. Which let's add this up. What's this calculator? 1150 times 9.8. I get 11,270 newtons. Okay, so I got Fg minus Ft equals ma. Okay, my two forces, I made down positive, up negative. Here I'm going to do things differently. I want to keep my positive going in the direction of my acceleration, all right? So this is positive and this is negative. So the sum of my forces is equal to ma. And I'm going to say Ft minus Fg equals ma. So let's start substituting. I started the problem here. I started to substitute. So I know 11,270 minus Ft equals 1150 times A. This one, I'm going to take 1,000 times 9.8. 1,000 times 9.8. I should do this one in my head, right? 9,800. That was silly. Newtons, okay? So Ft minus 9,800 equals 1,000A. So I have two equations. Now, we could bring this over, substitute in for Ft and go, all right? That's one way to do it, and that's how we did the last problem. I'm going to show you another way to solve, is I can add these two equations together. So minus Ft equals 1150A, and I'm going to add it to this, all right? So it's going to be plus Ft minus 9,800 equals 1,000A. So the Ft's cancel, and that's how we get rid of the tension force. And I say 11,270 minus 9,800. 1,470 equals, and I add those two together, 2,150A. 1,470 divided by 2,150 gives me an A of 0.683 meters per second squared. So that's the answer for the acceleration. And then to find tension, I just substitute. So I'm going to substitute that into here. 0.683 times 1,000 equals 683. Ft minus 9,800. Add 9,800. My force of tension, 683 plus 9,800. 10,483 newtons, and that's my force of tension. So what I did different here, one, I made the direction of my acceleration be my positive side, and then made that side negative. Perfectly acceptable to do. Here, acceleration up, so I made up positive, down negative.
again, perfectly acceptable to do. Get my two equations for both boxes. Solve for A by adding the equations together, which then eliminates my FT. You could solve for terms of FT and substitute. Perfectly fine. You'll get the same answer. That's just another way to solve it.
The advantage of a pulley. A mover is trying to lift the piano up a second-story apartment. In this picture here, there's the pulley, and there's the piano. I don't know if that's the best way to do it, but that's the way this guy's doing it. What force must he exert on the rope to slowly lift the piano's 1,600 Newton weight? You really don't have to do a whole lot of math with this, but just understand that if the weight is 1,600 newtons, and I have two strings, the tension is going to be split in half, right? So that means if I take 1,600 divided by 2, that will be 800 newtons of tension on each of these, which means I only have to apply 800 newtons of force to lift the 1,600 Newton weight. If I had a different pulley system with more ropes, I could even make it less. Like if I had a 3-pulley system, I could take 1,600 divided by 3, which then would be 533 newtons. So I could do even less. So the pulley system will determine that. But that's a quick way to deal with pulley systems. And that is all.